Okay, thank you. Good morning, everyone. Welcome. I hope that you are having fun in this day. The purpose of this lecture is to give you an idea of what a university lecture is like, and this is pretty authentic. It's not contrived. I'm not going to show you some amazing thing that will change your life as far as the topic goes. I'm just going to talk about a math thing, just like I will be doing in the fall in the calculus courses. The topic of the day is the Heaviside step function. So this is a topic that does end up in your Calculus 1 course that you take in 1A. So whether it's Math 116 for some of you, which is the course that I'll be teaching, or Math 117 for some of you as well, it's still a topic that's in both courses. So yeah, this is basically a lecture. I'm not started it yet, but I will in a second. The idea is basically I'm going to write some stuff down, I'm going to talk, and you'll ask questions, and I will answer them. I do encourage you to ask questions because you'll get more out of it. If you're wondering something, just ask me, and I will help you to clear it up in the way that you need it cleared up. I do sort of expect that you'll be taking notes, so what I write down, probably write down the same thing, and any side comments that you want to have for yourself. And then later on in the day, there's a tutorial in the afternoon, and it's going to be about this exact topic. So you might have already looked at the questions and seen that they're about the Heaviside function. This is the lecture, and then later in the day, you're going to do a tutorial. So, and there will be some TAs to help you with that. So if you have any questions before I get started, you can let me know now. And then as long as you don't, then I'm going to get started, and I'm going to take off I'm going to do a lecture hat, and then I'm going to put on the actual lecturing hat. Figuratively, I don't have actual hats. Okay, so if we're good to go, I will get started and sort of transition and pretend that it's a real lecture. Oh, yes, question.
In high school, when a teacher is giving a lecture, there's a lot of interaction between the students and the teacher. Does that happen in a university lecture?
Is there a lot of interaction between the students and the teacher? It depends on the person, right? So there will be with me, I think, as you'll find out. So like you've just done, ask a question, feel free to do so. And you'll see. You'll find out. It's going to be, feel free is what I should really say. Okay? Okay, now I'm going to start the official lecture. So we are going to talk about the Heaviside step function. So let's start with that. The Heaviside function is defined as this function that we're going to use the letter h to represent it, h of x. It's a piecewise function, which I'm trusting that you are familiar with. Piecewise function, you put this open curly bracket, and unsatisfyingly, you never close it. That's the convention. That always bothered me, but it is the convention. So this function is defined as 0 sometimes and 1 other times. And in particular, it's defined as 0 when x is less than 0, and 1 if x is greater than 0. That is it, and technically speaking, that is everything you need to know for today's tutorial. I see some hands. Do you have a question on the side? Yes? Wouldn't one of them have to be equal to 0? Because I have two open ends right now? Because it would be undefined for x equals 0. That's true. So this is a good point that you've brought up. This idea, I don't know if everyone heard, but the fact that, shouldn't we include one of these transition points? This function has certain values for x less than 0, certain values for x greater than 0. What about at x equals 0? Well, it's sort of a choice as to what convention one wishes to use. I've decided to use this version of it. There are other versions of this function where they will put an or equal to sign. Don't write this down. I'm going to scribble it out in a second or erase it. Or they define the function to be equal to a half when x is equal to 0, things like that. But I actually don't have a problem with leaving this function undefined at 0. It just doesn't have a value. 0 is not in its domain. And that's OK. Because the goal of this function, the purpose of this function, is to model an off-on behavior. So I mean, if you imagine the output of something you're programming to have a light switch, right? So if the input is a certain number, the output is 0, so the light is off. And if the input is some other number in some other region, then the output is 1, and so the light is on. And the idea of what happens at 0 is basically about, well, what is happening when I'm touching the light switch, and how is that energy going in? And for mathematical purposes and for modeling purposes, sometimes we don't care. I mean, there are areas of research where we really care about this sort of boundary behavior between states, but I don't for this. So we're using sort of a simplified thing, which is just trying to model before one thing happened, and then after a different thing happened. And that's it. So basically what I'm trying to say is I've made a choice to use this version. It also so happens to be consistent with the textbook that is used in calculus for this university. So we'll be consistent with the book too. Does that help to answer your question? Okay, excellent. That's a very good point. So the domain of this function is all numbers other than 0, technically. The range of this function is actually quite boring. The range of this function is only 2 different numbers. The output can be 0, the output could be 1, the output could be 1, and it could be nothing else. So I'm just going to graph this function in case that will help, which I believe it will. So here's the x-axis, here's the y-axis, 1 is over here, 0 is over here, and the graph of this function is literally, well, y equals 0 when x is less than 0, and y equals 1 when x is greater than 0. So that is the function h of x. This is y equals h of x. That's the graph. And I know some of you are used to having an arrow to show that it continues. I'm not going to really worry too much about that detail, so you may see other graphs that don't have those arrows. Don't worry about it. So that's the graph of this function. It's modeling an off earlier and then on later. If you imagine x to mean time, okay, so for negative t values or x values, time values, this thing was off, and then later it was on. And I mean, this on its own is the basic building block of what we're going to be doing. You can talk about h of x minus 5. It's a shifted version. So that's sort of like a timed something to turn on at 5 and not earlier. This is sort of the basic one. 0 is the center of the real line, so 0 is where things are going to transition. But you can certainly plug in something other than x into here. You can plug in x minus 5, so it's a translated version. You can plug in 3x, which isn't really that interesting, actually, if you think about that. You could plug in specific numbers to test out whether students have really got the concept of what this is. For example, you could plug in 3, and what would the output be? What would h of 3 be? 1, right? H of 3 would equal 1 because if x is greater than 0, then h of x equals 1. Well, x equals 3 would be in this category, firmly in this category. So what is h of negative 700? 0. Very good. Thank you. That's because negative 700 is satisfying this condition, so you look at that part of the definition of the function. So I'm making sure that you understand this to make sure that when I do the next example, it will certainly make sense. So are there any other questions before I go on to examples? Okay. Example. Sketch the graph of y equals h of x minus pi times sine of x. H of x minus pi times sine of x. So already I told you I can make things more complicated. It can look more complicated. Can you see over there with the balloons? How about now? Okay, great. Oh, see, I had to move the garbage can too. All right. So we're going to sketch this graph, h of x minus pi times sine of x. So it looks more complicated than h of x on its own, but it's still the same thing. H of anything is always 0 or 1, depending on what the input is. So as complicated as this can look and what you're multiplying it by, don't ever forget, it's going to be crucial to the understanding of the later things, don't ever forget that h of whatever is always just going to output a 0 or a 1. So even though this looks visually like 1, 2, 3, 4, 5, 6 characters, if you were typing it, it's either the number 0 or the number 1. It's really not more simple than that. The extra piece of that is that you have to think about where the input is. Is the input positive? Is the input negative? So just looking at h of x minus pi alone, will someone raise their hand and tell me, if I put in x equals negative 1, what does h of that stuff turn into? 0. You had your hand up. Yeah? 1 or 0? I can't hear you. I'm sorry. Pardon? Could you just shout? 1? Okay, thank you. So let's see. So we're plugging in x equals 1 to here. And then the argument that goes in here, 1 minus pi, is that positive or negative? Negative. 1 minus pi. I put in x equals 1, so 1 minus pi is actually negative, because we know that pi is 3.14 or whatever. So 1 minus pi is actually negative. So if I have h of a negative number, what is it? 0, right? H of any negative number is equal to 0. So it's not, I mean, this x here is now not actually the same x as it is here. It's like a substitution, right? You remember you have x squared, and then it's like, well, f of x equals x squared. What is f of x plus 3? And then everywhere where there was an x, you replace it with an x plus 3. So it's the same kind of thing. The x over here is not actually the same x as the x over here. This whole thing, it's about whether this whole thing is positive or negative. So as a numerical value, when x equals 1, 1 minus pi is negative. So this argument here is a negative number, and h of a negative number is 0, actually. So make sure that you're good at interpreting the input of a function and the output of a function and how those things interact. Does this make sense? Do you want any clarification or anything like that? Yeah.
So if x equals pi,
Correct, exactly. If x equals pi, then this function is just not defined. For the same reason that if x equals 0, this function is not defined. That's a very excellent point. Thank you for bringing it up. Okay, so we're going to sketch this graph now. And remembering that this h function is now basically, let's interpret this before we even draw the graph. Just this function right here. This function is sometimes 0 and sometimes 1, depending on whether depending on whether x minus pi is negative or positive. So how do we replace that in terms of a nice piecewise function? So I'm taking a step before I sketch the graph. Yeah?
h of x would be
Undefined at pi, yes, and?
and it would be negative if it's less than pi. It would be 0 if it's less than pi, and 1 if it's.
Exactly. Thank you very much. That's exactly right. So it's undefined. This function is undefined at pi because pi minus pi is 0, and h of 0 is undefined. And when you said this function would output 0 when x is less than pi and 1 when x is greater than pi, you actually did two things at once. You did an intermediate step, which was basically you plugged in x minus pi instead of x into the function. And what you did before you said x less than pi, you really thought to yourself, x minus pi has to be negative here. And you rearranged it and solved the inequality. So that's exactly it. That's right. And so, again, this is a sine function that's being multiplied by 0 or 1, and that's it, depending on where x is. And so we've actually got it. We figured out the dependence of x and whether you get a 0 or 1 accordingly. You know sine functions, you've heard about, you multiply a sine function by 3, and it's a sine wave with an amplitude of 3. You can multiply a sine function by 7, and it's a sine wave of amplitude 7. Well, you can multiply a sine function by another function, and you can sort of think about it, sort of structurally speaking, as a sine wave that has an amplitude of this. You can think of it that way. So this is a sine function that has an amplitude of 0 when x is less than pi, and an amplitude of 1 when x is greater than pi. And when you think about it that way, the graph becomes really easy to draw. I've got a sine function. I'll just draw this a little bit bigger. X is here, y is here. You know what a sine function looks like. And now what I'm going to ask you to do, temporarily, if you're copying down what I'm writing, which I sort of suggested that you do, for this very moment, don't. At this very moment, I'm going to draw it in red as an indicator that I don't want you to copy it down. Not yet. Once it changes color, I want you to copy it down. I think of this as a sine function that's being multiplied by this complicated thing. It's a sine function that's being multiplied by a partially hidden 1, or sort of something that I can sort of drape on top of everything to the left of pi and make it disappear, like an invisibility cloak from Harry Potter. I just sort of put over an invisibility cloak on everything that is on all the x values that are less than pi, because I'm getting a multiplication by 0. So it's kind of like the sine function was always there, but then I multiply it by this. And so this 0 kind of, oops, it just makes it disappear. So what really happens, let me draw in some tick marks here. Negative pi, negative 2 pi, 1, minus 1, things like that. What really happens is that everything to the left of pi gets multiplied by 0. Everything to the right of pi just stays there. So once I do that, again, I visualize it as sort of cover this up. And this is actually not here anymore because it got multiplied by 0. So I replace it with just that somewhat boring constant function, 0. So now, when I told you before, don't write what I'm writing down, now that temporary suggestion is now no longer in effect. So if you're writing stuff down, this is what I want you to write down. I've written it in blue so you can see it now. It's the 0 function. Please ignore minor variations in my artistic ability. This is a constant horizontal line here. And then at pi, something else happens. And I got that little open circle because this function is undefined at pi, just like that function is undefined at 0. Yes, question?
Should the start of pi go up? Sorry, the sine wave start going up at the beginning?
The question is, shouldn't the sine wave start going up at the beginning? That is a really good question, too. This is sine x, and what I think you're thinking about is sine of x minus pi. So we're not translating pi, and I know you showed me that you understand now, but it's a good question that I kind of want to tell everybody, so you brought it up, thank you. The question was, and no longer is, shouldn't we start by going up with the sine function? We're not shifting a sine function, we're suppressing a part of a normal sine x function, and then that's why I wrote it in the red, and then I said just put an invisibility cloak over part of it. Everything else just stays as it is. And to further answer what your thought process was led from, whatever it is, h of x minus pi, if this was sine of x minus pi, then I would agree with you that we would take a sine graph and move the whole thing over. But we're not moving the sine function over. We are moving where the h function turns on. And oh, yes? Okay, so the question is, as we were saying, this function is like off prior to 0 and then 1 after 0. This is a really good point. He said, what does that mean for this one, right? Like this amplitude idea. The way that I view it, I said amplitude so we can think of it easily as a sine function. This is a sine function over here with amplitude 0, which is kind of, it doesn't really look like a sine function, but it's a sine function with amplitude 0. And over here, it's a sine function with amplitude 1. But specifically with this on-off thing, I don't really want to think of it in terms of the amplitude anymore. I want to think of it as this is sort of like a pre-programmed timer to bring in a sine function at pi o'clock. If you imagine like you're trying to set some lights, some automatic lights for your house, you're going to go away and you want your lights to turn on at 6 o'clock every day, right? You're trying to type the code of how that's going to look programmed. You can talk about h of t minus 6. So these lights will be off before 6 o'clock and then on after 6 o'clock. Well, the only difference between 0 and 1, or 0 and a sine function, is that I literally, mathematically, I multiplied by sine of x. And what that means is sort of like you're carrying a specific function that you want to introduce at a certain time. Instead of just the number 1, this function is 0 and then 1 because 1 is an easy number to multiply by stuff, by other things that are more interesting than 1. So if I take h of x minus pi times sine x, it's kind of like I had a sine function that I was waiting to introduce to the world at pi o'clock. So that's on and off. So like the whole function is now on and introduced. So instead of a light switch that's just constantly on, maybe it's a light switch that's going to fade in and out, which would make everyone kind of nauseous, right? If the light was doing this, it's like everyone's happy, the light is off, and then at pi o'clock, if such a thing exists, suddenly I turn on a light that's doing this. sliding the faders down and up, right? So that's a little bit weird. And I also don't know what negative lights would be like. That's very interesting and possibly metaphysical, but I'm just sort of trying to give an analogy for the idea. Does that help? Okay, good. Yeah. Pardon? Oh, I'm sorry. You found a big mistake in my artistic abilities. I'm sorry. Yeah, this should go down to -1, and I didn't line these up properly. I'm sorry about that, and I very much appreciate that you pointed that out. So here's an edit, which goes in red, so you can see where that happened. So the scale is now fixed. Thank you for that. I did not notice. Sorry as well. Yes? Yeah, actually, this is a really good question too. So this Heaviside function, the question was, the Heaviside function is off and then on. Are there other functions that can be on and then off, or off and then on and then off again, or other way around? Yes, but you can build all of those from this one specifically. For example, plug in -x to h of x. H of -x, it would flip these basically. And so now h of -x, we can still use the same letter h to be talking about the same function. But that function with the -x plugged in would, instead of this, it would be this. So if you want to have something that was on and then later off, multiply it by h of -x. And you can add and subtract different things. And in fact, your question leads me to the example that I want to do. So let's talk about sort of even more complicated than what you said. This idea of taking a complicated combination of Heaviside functions and then interpreting them as piecewise functions. That's really it. So let's do an example now. Let f of x equal, I'm going to introduce a somewhat complicated combination of Heaviside functions. So if any of you wants to just shout out your favorite functions, go ahead. Okay. I just heard some laughter and some chatter, so it's okay, I got this covered. So 3 plus, let's put a sine x over here. Sine x times h of x plus 5 minus 12 times h of x minus 700. Okay? This is a random function. I don't know if you're able to tell. I made that up on the spot. It really doesn't matter what's in here. I'm trying to give you the structure, so you'll see what I'm talking about. And you'll especially see when you find out what the question is. That's not an example. It's just let f equal this. Okay, big deal. What do we want to do with this function? The request is to write f of x as a simplified piecewise function. Okay, I've written down the example, but I saw a hand go up a moment ago. Just, yes?
So instead of sine x with h at x plus 5?
Yep.
If you wanted it to say h times x plus 5, what would that look like? Because that kind of looks like h times x plus 5.
Oh, this is a really good question, too. You're talking about the notation and visually the way it looks. The question was, where I have h of x plus 5, and this is the way I said it, and this is what I mean. When I have h of x plus 5, how do I know that that's not the same thing as a number h multiplied by the expression x plus 5? Well, the reason is, functions have names, right? So if there's no number called h right now. Just in the same way there's no number called sine, right? I could talk about sine of x, but I can't talk about sine and then not say anything. Right? Sine is the name of the function, so in the same way, h is the name of this function. If I wanted to multiply h by the number x plus 5, I wouldn't be able to, just in the same way I wouldn't be able to multiply the number sine, because it's not a number, by the number x. However, in math, sometimes some numbers end up being called the letter h in other contexts. This is not one of those contexts. So within the context of this lecture and today, when you see the capital H, it literally is the name of this Heaviside function. So there's no such thing as h on its own unless I'm just sort of speaking generally about, well, what is h? It's this function, right? It's not a number that gets multiplied by x plus 5. It is a function that gets x plus 5 plugged into it. And to finally answer the last part of your question, you said, how would I have h times x plus 5? Well, it would have to be h of something. So I could have h of x plus 5 times x plus 5, which would look very confusing, but it would be theoretically possible to write such an expression. That is a really good question, is the functions, the notations, and all those kinds of things. So I appreciate that you asked that. Well, let's look at this example. Here's a function. It looks complicated. It's a bunch of different Heaviside things. Write this as a simplified piecewise function. Yes, question? Exactly. We can break it up into 3 if-then piecewise functions. Or, furthermore, I'm going to take your idea. There's 3 because, well, are there 3? There's really 2 if-then things, right? This thing, this h of x plus 5 is sometimes 0 and sometimes 1, based upon whether x plus 5 is negative or positive. This one over here, h of x minus 700, is a different piecewise function that is sometimes 0 and sometimes 1, depending on whether x minus 700 is positive or negative. So you can sort of think about different functions, and that's going to be kind of complicated. I want a simplified piecewise function, so this is a singular. I want one function with different cases. And the first thing that I noticed, based on what you're explaining, is this thing changes what its output is going to be depending on where x is relative to 700. I'll say that again, just in case you happen to not to be listening. I'll just say it again. This h of x minus 700, it changes what its output is going to be depending on where x is relative to 700. So I know in my piecewise function, there's going to be a if x is less than 700, and another thing if x is greater than 700. But at the same time, this one over here, h of x plus 5, that one is changing its output depending on where x is relative to what? Not 5, negative 5. You know, mathematicians would prefer to see x minus negative 5. It's easier to understand in the context of Heaviside functions. You write x plus 5, but really it's x minus negative 5. The negative 5 is the 0 of that function. So that's where the transition occurs. So there's a transition at negative 5. There's a transition at 700. So what I'm going to do first is focus on that thing only. That thing, and that's not very precise of me. So I'm going to focus on this aspect of the fact that there's a piecewise function that is changing what its output is going to be depending on where x is relative to 5 and also where x is relative to 700. So I left that whole first part blank. I'm only focusing on one piece of the problem at one time right now, breaking it down into the different possibilities of what x could be. And I've broken it down into all the different important intervals where if I'm within this interval only, then what this output is will not change. There's no like x equals negative 7 or x equals negative 30. Like those aren't different from each other as far as this output goes. It's really x less than negative 5, x between negative 5 and 700. The notation there, you could also write it as negative 5 less than x less than 700. There's a choice of notation. It means x is between negative 5 and 700. And here, it means x is greater than 700. And those are the only transition points. So this is one step of this problem, which I focused on separately from another step in the problem, which is to write the details of what this turns into to answer the question of the simplified piecewise function. Yeah? That's a good question. The question is, am I really picky about the notation? Like, should I say x less than negative 5, or do I care if you say x is an element of the interval from negative infinity, comma, negative 5? No, I'm not picky. I'm not even using the same kind of notation in the different pieces. This is still true and it's still correct. So yeah, I'm not picky. As long as it mathematically is sensical, then that's okay. Now, I'm going to fill in this. And I'm going to tell you a secret about thinking, and honestly, this is going to help you if you decide to accept this sort of friendly advice, then it will help you for the rest of your life. It sounds like pretty cool advice, right? It's about how to approach problems and how to even approach writing down your solution to a math problem in general. I could do the following. 3 plus, I could start writing it as 3 plus sine of x times, and then I pause and I go, what is this times, right? What is this multiplied by? H of x plus 5. Oh, what is that, negative or positive? You know what, I'm not going to do that right now. Because what's going to happen is I'm going to do that, I'm going to be focused on like 3 different things, and I'm trying to switch between them all at the same time. I'm focused on copying stuff down, looking at different things, interpreting and solving a separate problem, and then writing it and transcribing what I figured out, and then going back to copying more stuff down, minus 12 times, and then thinking, well, what is h of x minus 700? What do I replace that with? That's really inefficient. And what I'm going to do is, it looks ridiculous, but I am going to not spend time on that at this very moment. I am going to do what looks to be less efficient at first by literally, almost literally, copying and pasting the same expression in all 3 lines. And I like to think of these moments as a break from having to think. I know that you're, I don't want to copy stuff down. Do I have to write this, right? It's a break from thinking. I just copied. It's easy to do. That's one mental task of copying stuff. That's easy to do, and it's a break from having to think. But now I look at this, and I say, now that I've got it written down, I don't have to worry about flicking my eyes back and forth every time to, like, if I started writing and then I paused and figured this out, and then I continued and then put it in and then figured out the next thing and copied. I don't have to go through that whole thing. What I can do now is focus on that whole idea of interpreting whether h of whatever is 0 or 1. Remember at the beginning of the lecture I said, it doesn't matter what you plug into this function, x plus 5 or x minus 700 or whatever it is, h of anything is just a 0 or 1. It is not any more intimidating than that. Even though it's h of x plus 5, it looks very complex. Like I said before, this is really just a 0 or a 1 depending on where x is. This whole expression that I now have my hand extending over. So now let's start answering that question. What is h of x plus 5 when I am in that region x less than negative 5? We have an answer. Say that one more time, please. We're going to have a negative number in the input, so 0. Yeah, I agree with that, right? X plus 5, if x is less than negative 5, some number like negative 5.6, negative 800,000, any number to the left of negative 5, if I add 5 to it, 5 is not big enough to turn the whole thing positive. It's this whole expression inside the brackets, x plus 5 is negative in this region. So because, here's what I'm going to do. I'm going to say x plus 5 is less than 0. Just the argument. I circled the x plus 5. I said that's less than 0, which means when the argument, the input of the Heaviside function is negative, the output is 0. Again, it's not different from that same h function. H of something is 0 or 1, depending on whether that something is positive or negative. H of this is 0 because this is negative in this region. So we replace this whole thing with 0. And I just wrote it right on here. So it wasn't really a waste, because this is a step that I need to take in order to solve all these. There's 6 of these h's that I have to replace with 0s or 1s. That's the only thing I have to replace them with. Yes? This is absolutely correct. I don't know if everyone heard, because it's a large room, and I have a microphone. So I'm going to repeat it for everyone. Everything you said is completely 100% correct. So what was said was, now we can do the same thing for the other h in this line. Well, x minus 700, when x is less than 5, is definitely negative. So the argument of this h function is negative here. And so h itself is 0 here in this region. So this line simplifies to a 3. And that last part that you said, that first piece simplifies to a 3, I don't even want to think about that yet. That's a later thought process of the simplification. So actually, although you're correct, there's nothing wrong with it. I want to continue to highlight this idea of thinking of one thing at a time. Not that you have to, but this is the way that I wish to present it. So yes, I agree with you that 3 plus 0 is still 3. At the moment, I don't care, because in the moment, I'm in figuring out whether h is 0 or 1 mode. So I'm going to stay in that mode for a while. And in some senses, it's easier on the brain to sort of be in one mode. And I'm not saying you need to limit yourself to always be stuck in one mode. Be ready to be flexible, of course. But as far as an organized approach to solving the problem, I want to continue to suggest that I don't care what this simplifies into at the moment. In the next step, I will care, and I'll do the cleanup and the simplification. So everything you said is right, but you went over and above what we need to do right now. So now let's do the same thing in the next line. X plus 5. I'm focusing on this piece right here, h of x plus 5. X is between -5 and 700. So the key piece of information is that x is greater than -5 now. The fact that x is less than 700 is less important to me. X is greater than -5, so x plus 5 is now positive. So if I input any number to the right of -5, x plus 5 is positive, so h of that positive number has to be a 1. So I'm going to do something that, using certain colors to make a suggestion. The argument, oh, that doesn't look good where I put the equal sign. Sorry, I'm going to fix this. The argument of this function is positive now in this region. So now the entire function here is 1. And actually, if I continue moving down the h of x plus 5s, I can do the same thing here. If x is greater than 700, x is still greater than 5. So again, if x is greater than 700, then x plus 5 is still positive. So h of x plus 5 is still 1. So I'm going to write a little bit less detail of the argument and all this and stuff like that. But the fact is, h of x plus 5 gets replaced with 0 and then 1 and then 1 in that order. It's kind of like the h of x plus 5 was 0 before -5 and then 1 after. So if I sort of visually go down, that's I can see if I go across the real line that this thing was off, and then I got to the region where it was on, and then it stayed on later. That was that. There's 2 more h's here, and this one's actually a little easier because it's x minus 100 instead of plus with the subtraction of the negative and things like that. X minus 700, positive or negative in this region? Negative, which means that the entire h of all that stuff gets replaced with a 0. And finally, when x is greater than 700, this h of x minus 700 gets replaced with a 1. Those are all the pieces we need to finish solving this problem. We have one more thing we need to do, which was the earlier suggestion of simplifying the fact that 3 plus 0 plus 0 equals 3. You know, the fact that 3 plus sine x times 1 minus 12 times 0 is something specific. So now I have to do the simplification step, which I will do now. And it's actually a very fun and rewarding part because we went through the difficult part. And now we can just write out the simplified answers. But for a brief moment longer, I'm going to stay in this mode of thinking of let's take care of one thing at a time. So I'm going to write the cases here and then fill in the simplification steps. Still focusing on one thing at a time. Now I'm going to fill in the simplified steps. Now I'm ready. I've set up my situation for myself to simplify what I have to. 3 plus 0 plus 0. Cool. Now we get to do the fun part. 3 plus sine x minus 0. 3 plus sine x. And finally, the very bottom case, 3 plus sine x minus 12. 3 plus sine x minus 12. So, 3 minus 12, negative 9. So sine x minus 9. There it is. So in addition to solving the example, I also kind of wanted to suggest to you a way of approaching problems. Yep? If we saw a question like this on a midterm, how much time would I spend you to spend on it? Not much, actually. I spent a lot of time because I'm in the midst of teaching it. But honestly, this is easy to do if you kind of follow this idea. There is a little bit of, is this 0, is this 0, is this 1? Like that takes a bit of time. But setting it up, figuring out the transition points, and doing this relatively quickly. Where are the transitions? Just do that and put them in order. Copy the thing down every time, which is what I would suggest. And then replacing the zeros, simplifying. Honestly, it doesn't take more than 5 minutes or so, even though it took me 20, you know? Yes? So the question is, if you're on an exam, do you need to write each step, or can you just write down the final answer? In general, this is, pardon? Oh, yeah, so do I have to write every single thing on the left side? You don't have to solve everything exactly the way I've written it. This is my suggestion as to how you write it. Write it in a way, here's my rule of thumb as far as what do you write on the midterm. Write it so that if you were reading it later, you could make sense of it. So teach it to yourself. Teach it to your future self who forgot. Think of it that way. One day I'm going to forget. Let me teach it to my future self so if I read it, I know what I was doing. Yep? How important is the notation? Do we have to do the comma if, or can you just kind of 3x minus less than a, or semicolon? That kind of notation, I would say, is not super important. If you decide to put a semicolon, 3 semicolon x less than -5, this semicolon x between here and here. I'm not too concerned about that. Again, it's sort of, if it's right and it makes sense and it's logical, then I'm okay with it. But the kinds of notation that we get really picky about in math is where people will like, there's a function f equals whatever, and we say find the derivative, and then they say equals, and then they write the derivative. And you're like, you're saying f equals its own derivative? Wait, that doesn't make sense. So use the symbols that you have appropriately. But if you choose to use a slightly different way of using words, putting them together and stuff like that, that is okay with me. Yep? Pardon? Efficiency? How important is efficiency when you're doing questions? I'm not sure how to answer that. Like, you mean this way I'm suggesting? You don't have to do what I'm doing, but I think it helps. No, you don't lose marks if it's not efficient. Okay? There is one more example that I need to do because you have a question about it on your tutorial. So not to sort of crush your questions or anything like that, but your questions are not really about the topic at this point, and we do need to stay on topic. Okay? There's more math that needs to be covered here. And it's just one more example, and it shouldn't take too long. This question we just did, we started with a complicated expression of Heaviside functions, and we converted it into a simplified piecewise function. What I now also want to show you how to do is to start with a complicated piecewise or a simplified piecewise function and turn it into an expression in terms of Heaviside functions. There is benefit to both procedures. If someone gives you this, you can understand what it means. It's very readable as a human being. But if you start with the situation that you understand as a human being and you need to program it into a computer to assign how your lights are going to be working, you want to convert it into something like that. So I want to be able to go the other way. That's what this is. So let g of x equal the following piecewise function. X if x is less than -1, 3x if x is greater than -1. So I'm not going to make it super complicated, but it's just a transition kind of thing where there's an initial function and then there's a later function. So you've got some scenario where initially everything was just x and then later everything was 3x. So the question is, write g of x as I'm going to put the word simplified again, simplified expression of Heaviside functions. And then once we're done this example, it will be lunchtime. You could probably, I'm just thinking out loud now while I'm erasing and just thinking about this topic and how it relates to lunch. I mean, you could write the schedule for the day as a piecewise function and then turn it into Heaviside functions. So you can sort of like, when is lunch, or what is lunch? We got lunch multiplied by h of x minus 1230. Something like that. I'm sorry to be silly about that. Anyway, the erasing is done, so let's get to this example. We've got a transition at -1. So we see a transition at x equals -1. So we use h of x plus 1 to capture this transition. Or I'll just say this. And these words are a little vague, but the math will be clearer. So I'm just sort of giving you some context as to what we're about to do. So we see a transition at x equals, I didn't write the minus sign. I remember saying it. Somehow it disappeared from, it never occurred, in fact. It might have, the negative sign may have had a Heaviside multiplying it. It appeared now. Okay, this is my attempt at being funny, I'm sorry. Okay, so sorry about the edit, the correction, there it is. So there's a transition at -1, so we use h of x plus 1 to capture this. And what I mean by that is we're going to look at it like this. I'm going to look at it from left to right. And this does come back to the earlier question, like how do you get something where different things change? We start with a piecewise function, write it in terms of Heavisides. And I'm going to say right now, there are multiple ways to solve this. I'm going to show you one way that basically works no matter what, and there are other ways that also work no matter what. I've just chosen one of the methods. So if you decide to try another method that you thought of on your own, and it's not what I do, if it works, it works. So think about that. There's ways of multiplying functions or plugging in negative values instead. You can play around with that as much as you wish. But what I'm going to do is say, okay, g of x is x first and then 3x later. The way I think of this is that just like we had the sine function way earlier in the lecture, we had that 0 and then the sine function later. I'm going to think of this as an x function that's just sitting there on its own and everything's fine to the left of -1. And then I'm going to add in a suppressed 2x at a certain moment. 2x specifically. So I'm looking left to right on the real line. Prior to x equals -1, there is just x. And what I'm going to add to that is something specific times h of x plus 1. Again, I'm doing this structure thing. I'm sort of looking at the big picture. That if I have this, I haven't filled in what's in those brackets. But if I have x plus some stuff times x plus 1, I've modeled a certain part of that behavior completely correctly. That is, to the left of -1, that function is certainly x. It doesn't matter what's in those brackets. If I'm just at the left of -1, then the function I've written there, even though I haven't finished writing it, is going to satisfy this piece. To the left of -1, the function is just x, just like it's supposed to be. Now if I transition to the right of -1, it matters what I put in those brackets. So to the right of -1, I've introduced an extra thing. And what did I introduce? I sort of gave it away. I didn't mean to, but maybe you forgot. So does anyone know what we have to introduce here? I heard x2x, because two different people said it, sort of 2x, 2x. It was neat. It's sort of doubled. Yes, 2x. 2x, but I'm going to say one last thing about just the way of thinking of things. It is going to be 2x, because to get from x to 3x, you need 2 more x's, right? So, but a better way to think of it, maybe not better, but a more general way of thinking of it, is whatever the new thing that I want to replace it with, minus whatever was there earlier. And this seems convoluted and long-winded, but again, this is more generalizable to just any approach. Yeah, it's 2x, but I really think of it as 3x minus x. I brought in the new thing that I'm swapping out with whatever was there earlier. Yes? So the question is, isn't the function not supposed to be defined at -1? Because it just isn't, right, with Heaviside function. But this function gives a value at -1. I didn't give this function a value at -1. I mean, I do have the expression x equals -1 here, but this isn't about the domain of the function. I see a transition at that value along the real line. So when I'm talking about x here, x -1, it's not like it just disappeared from reality. It's still there. It's just not part of the domain of the function. So to the left of -1, the function was doing something. At x equals -1 on the real number line, there was a transition. So I'm not trying to say this is part of the domain of the function when I say this. This is what you're talking about, right? This over here? Oh, okay. No, I didn't understand your question properly, but I do now. You're saying x equals -1 should not be part of the domain, but it is part of the domain of this. That is a really good question, and the answer to that question is that if I have a function which is the sum of two different things, the domain of that function is the intersection of the domains of the two things I'm adding. X cannot equal -1 because of this, so I just can't put in -1 to the whole thing at all. Because I could put in x equals -1 here, of course, but -1 plus something that doesn't exist. So the domain is still carrying that x cannot equal -1 with it. That is a really good question, and I'm sorry for misinterpreting that first. Okay, so question answered? So the last piece to simplify it, oh wait, just one thing I wanted to say. What I was just explaining here with this 3x minus x, I think of it as new minus old. The new thing swaps in, right? So just like I'm going to be pulled away here, and then someone else is going to be here later in the day, minus Andrew plus whoever's next kind of thing. So we can simplify it, one moment, to this, of course. And I know that you were definitely smart enough to have done that all in one step. But it's a structure that I'm trying to point out because later on the tutorial you'll see other things that don't obviously, it's not so obvious what you put there. So there's the simplified version, but the concept is you can just add the new thing minus the old thing times the thing that transitions at that point. Okay, so one more question? Yes, exactly. So in the interest of time, I did not do a piecewise function that had 3 pieces. But if there was another thing, like another transition at 5 or something like that, the question and correct suggested answer is I would have to put another plus, a bracketed, the third thing minus the second thing times the transitionary h of whatever. Yes, you're absolutely right. And you'll try the tutorial, and the TAs can help you through that. And you can check with the solutions later, or the TAs who have the solutions. Whatever it is. So there's not actually any more time for questions, so I'm sorry. I will be at the lunch, though, so if you want to talk to me, I'll be around. And have fun with the rest of your day. Thank you.